Okay. So let's go over these problems real quick and discuss them. So the first problem is this one, ball game. And I'm gonna go over my solution first. We'll go over the problem. So for this problem, you have n balls that are placed at distinct coordinates. And so the distinct x coordinates, so none of them overlap, but also it's guaranteed that the coordinates are greater than 0. So there's a hole present at the origin. Each of the balls are moving toward the hole, and they're moving. It gives you the speed per second. If multiple balls collide, reaching the hole, they merge into one ball, taking the maximum speed of the initial balls. Determine the number of balls that will reach the hole, considering all possible collisions along the way. Note that collisions do not occur at the hole. Thus, if multiple balls reach the hole at the same time, all are counted separately. So let's go into. I would do this. So, first observation is that you have some hole here, and you have like just a line, really. It's a one-dimensional line where you'll have so let's say this is at 0. So really these are like some position along, like this is 10 units along. This might be 20 units long. So each ball can only be at a distinct location. So you could have a ball, let's draw a ball here. You could have a ball here, ball here, a ball here. Really, a ball could be anywhere, but you can't have one over there. We also know the direction of travel of all the balls is in this direction. They're all going to reach the hole. And the question really is how many, determine the number of balls that will reach the hole. Okay, so at most n balls, or let me change the color there. At most n balls could reach the hole. Now, there may not be n balls that reach the hole because some of these balls may collide. They all have some type of speed, and so they may collide at some point. So the collision is kind of like this. Like, there's two observations for collision, really, that I think are useful. The first observation is that if you have a ball that's moving quite fast, let's say it's 10 units per second, and you have another ball that's moving slower and it's only moving 2 units per second. And a quick observation is that since I drew these balls based on their spatial relationship to each other, this one is more to the right, but they're all heading to the left. This ball, so let's say this is A and this is B, these will never collide. As a simple observation. So when could they possibly collide? Only when you have something like this. And in this case, they will collide. But the next thing that's important is the following. So two balls may collide, but you want them to collide, they must collide before reaching position equal to 0. That's another observation. Okay, so given two pairs of balls, how might I find this? Given two positions of balls, how may I figure this out, right? So given A and B, how can we do this? Well, the ball has its original start position, and it's going to be moving to the left at some speed. Let's call that S. And it's going to take some time, right? So what I want to know is, when are these, this is equal to position, right? X, the start position, the initial position, plus, but the speed is negative, so I just do minus. So minus the speed times the time, that's the position it'll be at each instance of time. So 0, 1, 2, what position will it be at, right? It'll be getting closer to the origin because I'm subtracting. So it's going to continue to get until it reaches position 0. Now, these balls collide, so this is when they collide. Say, this is the collide written as an equation. And they'll collide at this point in time. So you just have to solve for t here. So oops. Okay. So this is the time. Okay, so this is what you want to solve for. And basically, if t is greater than 0, that means they collide before they reach the origin. So that's an important observation. Another important observation is that, well, this is an important observation because now we have a way of actually calculating giving two pair of balls. But there's another quick observation, which is that if I have two balls, okay, so what I want to mention here is that this ball collects with ball 2, or let's say this is A, B, C. So ball B collides with A, but the collision of B and A, it may happen at 10 seconds. Yeah, it may happen at 10 seconds. But C will collide with B. So one important observation here is that when C collides with B, it's going to continue to move at 10 units per second. So in a sense, since it's going to continue to move at 10 units per second, that means I can calculate when it will collide with A. And maybe it collides with A in 7 seconds. So technically C will collide with A before B will even collide with A. But the argument here is that anytime you have a ball C and it's going at some speed, all you have to do is look at the balls to the left of it and calculate, collide with them. But let's suppose it was different. And so suppose B doesn't collide with A till later. But suppose that the 10 seconds when it collides with it, it'll be after the origin. So then B doesn't collide with A in time. So A and B will be left in the stack. So you could have so you could basically have A and B are both in the stack. But then C comes along and C will collide with B in time, and then you'll pop that out, and then you'll pop out this one, so you end up with a stack like that, you'll put C in it. So basically C could end up colliding with both of those, but it could be different. It could be the case that you originally put A, but then you put B, so B collides with A in time, and then C collides with B in time. So it's whatever, but what you can see here is that you can use a stack. You just need to look at the last elements and determine if it collides with that. So one key, now of course this will only work if it follows this invariant, which is the following. Given a stack B and C, this is the invariant bit. If C collides, so say collide B and C, let's say that this is false, and when I say false here, I mean it doesn't collide before it reaches the origin, but for some reason A and C collide, so I'm going to argue that this is impossible. This is impossible. If A and C collide is true, that means, and B and C don't collide, that's just not going to be possible here, right? Because B and C don't collide kind of means that, you know, they're going at some speed, but if A and C collide, that means it's going fast enough to somehow collide with A, yet it doesn't collide with B, right? That doesn't make sense. That means either B had it collided with A, or C collides with B and it collides with A. But it has to be true. It has to be the case that C collides with both A and B. And in that sense, you can use a stack. So you just have to check the collision. So if we look at the code here, basically we have the vectors of the balls, which has the speed, the position and the speed, because we want to sort based on the position, and then we have the speeds. We have the those two, so we just read in everything, create the objects, sort them based on their position, so we process them in a specific order. It's kind of a pattern for greedy problems is when you sort it and you go through a specific order. You have the stack. You have to check if the stack is empty. So for each ball, you check if the stack isn't empty, and then you check if it collides with the ball on the top of the stack, which you can just represent with the index. And if so, you pop and then you push in the stack. And so your answer will be stack.size. Two facts here. One ball, the minimum number of balls that could reach the origin is 1. The maximum number of balls that could reach the origin is n. Those are kind of our lower and upper bounds. And the collide function here is just going to be this Boolean that takes in I and j, where there's a specific pattern that I is guaranteed to be at an earlier position than j. That is, j is further from the origin. So first thing you have to check is the speed, right? The second ball is not going to collide with the first ball if it's not going faster. And if it is going faster, then you just calculate the t, the equation that we calculated before. And then you calculate the position by plugging in this t into, you could do the first ball, and then check if the position is greater than 0. That means it collides before. Okay. Let's go to the second problem. So the second problem is sequence search. So it gives you a sequence, and it wants you to find the k-smallest element of sequence x. You can see it can go real large. So yeah. So here's the thing for this one. So let's look at what the sequence looks like. It tells you how the sequence is built. It's going to start with a 0, and then it's going to be an A, and then it's going to be a B plus an A, and now it's going to build it based on a certain pattern. So if you follow the pattern that it gives, it's going to produce the following numbers. That is, it'll produce, sorry, I did this wrong. It should be B. So it tells you, the first 3 elements are like that. But then it's going to build them a certain way. So it's going to take B plus A minus 0. So you end up getting B plus A. And then you're going to end up getting 2B. And then I'm just going to write out the pattern. So if you explore it, you'll see it real quickly as well. 2B plus A, 3B, 3b plus a, 4b. Okay, I think that's far enough out. Let's write the index for this. Okay, so essentially all of these a's happen at an odd index, and the b's happen in an even index. What you could say basically is that b increases at each of the even indices. So it goes from 1b, goes from 0b, 0b, to 1b, to 2b, to 3b, to 4b. So yeah, it increases at each of them. And then for a, it's basically the same thing. Like it's going to be 0b plus a, 1b plus a, 2b plus a, and so on. The question is, how do you find the kth smallest? So here's the idea. Kth smallest just means that the number of elements that are smaller than it are equal to k. I don't know, like, so say k equal 1. That means there's, well, k equals 1 would be what? So I think k equals 1 corresponds to this, so that means there's 0 elements smaller, but like, yeah, so k, so smaller. So it kind of leads to this idea that, oh, what's up? Okay, so so you just want to count the number of elements that are smaller. Alright, so how can you count the number of elements? So, one idea you might think about real quick is, can I binary search? That's kind of a question. Can I binary search? This could be something you could try. And could you binary search? So you just, binary search would mean I would just take a guess, and is it right, is it wrong? If I'm going to binary search, if you look at the constraints, this is 10 to the 9, right? So worst case, I think it might be, you could say 10 to the 8. So you could set low to 0, I don't know, high to 10 to the 18, I think. 10 to the 18 just because, like, you could have 10 to the 9 times b, and b could equal 10 to the 9. I don't know. Something like that. But then you binary search, but for each binary search, the thing that you need to be able to do is you need to be able to count how many terms there are in this sequence which are smaller. So if we split these, so for instance, how could we count the even number terms? Well, it's not that difficult. Like, take the take the value of this. So say you're guessing some value x, right? Let's say x is equal to 4b, for instance. If you take this value x and you divide it by 2, what are you going to get? So let's say b is equal to 4. So you have 16 divided by 2. I'll give you 8. Okay, so take this and divide by b. You'll get 4, right? So, yeah, so So we'll look at an example. So let's say I have 4b, and let's say I divide by b. That will get me 4. So the thing here is that how many b terms are there? There's 1, 2, 3, 4, 5. So there's 5. So you have to add 1 to this to get the answer, to get the count. So what you can do instead is you can say, given some value, I divide it by b, and I do floor division, and do plus 1. And this would be even count. So I can define even count to be that. Okay. So what else can I do? You can also count odd. So how do we count odd? How would I count odd? So let's say you have plus a. Okay, and you want to find the count. What if you did this? I think this is how I did it. So yeah, I'm forgetting a bit what I did because I did this a few days ago. But yeah, so this is what you can do. Divide it like this, and this will give you 3. But 3 is not the correct answer because it's 1, 2, 3, 4. Sorry, 1, 2, 3, 4. So it's off by 1. So for this, you'll take x minus a divided by b, take floor of that, and plus 1, and that will equal odd count. And so if you sum these two together, they so if you sum even count plus odd count, and let's say it's smaller or equal to k, what does that mean? If it's smaller or equal to k, that means it kind of satisfies it. I think you're going to want smaller than k. No, you're going to want smaller or equal to k. And then so you just return true, true, true in the Boolean. And you just want to return the last case of true. Okay, I think that works. Let's look at if that's the solution I use. Yeah, count for mid divided by b, floor mid minus a divided b. You'd have to check that mid is greater than or equal to a. Oh, I did this. Oh, interesting. Huh. But I think it would work if you did less than or equal k as well. Like, yeah, I agree this would work. Oh, you know what? It wouldn't work if you did less than or equal. That's true. So it has to be count is less than k, and then you just increment by 1, so it gets the first instance. The reason why is because there could be a range of values where the count is correct, but it's not the answer. Yeah, I would say look into that. But this is the basic solution. It should get you far enough. Then look into a pattern. I remember I looked into it, and you see why that's the case. Shooting. Sure. Okay, we're getting some of these ones now. For this one, this is a hard version of the problem. The only difference between this and the easy version is the constraints on in, notably in this version. So we have ARC and crypto were competing in a shooting game. You're given a matrix A of size n by n. Basically, he took a shot at this cell, Crypto took a shot at this cell, otherwise both players took a shot at the cell. For each cell, you want to calculate the score for the score is calculated by taking two pairs of coordinates and then taking the max as you take the difference between this and this, between the x and the y. And the score of the player is the sum of all scores shot by that player. So then you want to take RC score minus crypto score accordingly. One trick observation is 3 doesn't matter. We're going to ignore 3. I argue 3 doesn't matter because both at any cell location, if you calculate the score of all the other players, both players will get the same score to this. So when you subtract, it'll just cancel. You do RC score minus crypto score. So really, you're only interested in the 1 and the 2. That's just a quick observation. What else? So essentially for this one, really I just used them. I learned this trick for it. If you're taking the max of and there's a Manhattan trick which it says that this is equal to where S is basically a coordinate transformation and T is a coordinate transformation, where these coordinates are correspond with these two values. And there's a very nice visual for this as well. If this is my X and Y, then think of X plus Y as your bisector line, and then X minus Y is like the bisector going through here. So now you have your S and your T. So it's kind of like the coordinate system is rotated 45 degrees clockwise. And if you do that, the calculating the max in this coordinate is use the max, but in the S and T coordinate reference frame or whatever, you just need to calculate the Manhattan distance. And so this simplifies the problem because now you can just solve it with now you just need to solve this, which is a much easier problem to solve, to calculate. So we'll focus on one person's particular score. So let's say you're trying to calculate the score of one individual. How would you do it? Well, if we're dealing with the S, let's say the S coordinate values, what we're going to do is we're going to take everywhere where the grid of RC is equal to 1, because let's say this is RC, I believe, we'll just sum them up. So we'll just, or we won't sum them up, but we'll have a bunch of values here, and we'll sort them. But these are the values of the S. These are the values that S can take. And it's kind of linear, because at the top, that Manhattan distance, by the way, it kind of gives us a hint that we can do each dimension. We can solve the two-dimensional problem by solving two one-dimensional problems. We can do the S dimension first, and then we can do the T dimension. Independently, they can be solved and summed together. So, also, we're doing this. You do this for each ij. So yeah, we are going through each cell. So we already have a time complexity of O times nm, but then we need this to be pretty fast. So let's say this is sorted, and then let's say also you calculated a prefix sum. Something like that, right? You also have a prefix sum, and you have this thing sorted. So now, how would you calculate the difference? So let's say you know your current S. So how could I calculate the distance, the score along the S dimension? So I'm going to calculate the score along the S dimension. So here's how you can calculate it. So given your current S, you can take your S array and you can binary search. So that means you have like a log in or something time complexity, I don't know, roughly, and your binary search, and then it'll find like a particular location, and then using the prefix and the suffix sum, you can calculate the total distance to every other s coordinate given the current s coordinate. And yeah, so that doesn't extend the time complexity that much more. And yeah, and then you just have to figure out the math to be able to do this. This is why you need the prefix. But I'll just write down the basic idea is, given your current value, let's say your current value is v, to be able to calculate the prefix, all you need to do is do v times something like position, I think you do have to do +1, minus the prefix pose or something, and then that will calculate the prefix distance, and to calculate the suffix distance, you need to take take the total sum minus pre-pose, and that gives you the total distance of this from over here, but now you need it from over here. So you need to do minus n minus pose, something like that. Roughly something like this. I'll let you derive it, because there are specific, if we go into the code, I'll just show real quick. So yeah, so you basically do this, you break them down into the x and the y coordinates, and the prefix sum and the prefix for the y. So you push back the value, but you push back the transform coordinates. So you do the same thing for the I. So you do the calculation now, and you take in the specific one, and this 0, 1 just refers to the different person, RC, and this other individual crypto. And then these array x and p sum x, and then you also do this, and then I do this. So pretty straightforward. And then here you just do the binary search. So here does the binary search, where you're just getting where the array value is less than min. And here you do have to deal with a bunch of like edge cases, like what if low is greater than 0, 0, you know, so on. So you have a bunch of edge cases to handle, quite a bit actually. So you have to make sure you handle those appropriately. Okay, but the rough idea was the Manhattan trick. This one, I'm running out of time. This one I'm going to do afterwards, but this one's just going to be dynamic programming. Well, yeah. Now we'll go over this one real quick.